High-quality AI image generation is everywhere you look these days, right? It feels like these models can just whip up anything you imagine.
It's really exploded.
But have you ever stopped to really think about how they do it? I mean, we hear a lot about diffusion models, obviously.
Yeah, they get a lot of headlines.
Or maybe those massive autoregressive transformers that feel kind of like language models, but for pixels. But is that really the whole story?
Well, that's the interesting thing. You're right. The generative AI space, especially for high-res images, has been pretty much dominated by diffusion and these discrete autoregressive methods.
Right.
But there's this other foundational family of models. They've been around for a while, but often, overlooked in this latest wave. They're called normalizing flows.
And that brings us right to our deep dive today. We're looking at a paper that makes a really compelling case for normalizing flows, basically showing they can absolutely compete at the highest level of image generation.
Exactly. Our source is the paper STARFlow, Scaling Latent Normalizing Flows for High-Resolution Image Synthesis. And it comes from researchers at Apple.
Okay, so our mission here is to really unpack this. What is STARFlow exactly? How did these researchers crack the code, to make normalizing flows work at this kind of scale?
And critically, how do the results stack up against the models that are getting all the attention right now?
Yeah, and maybe most importantly, what does STARFlow success tell us about the future direction of generative AI? It's that feeling, when you get your hands on a new research paper and just want to peel back the layers.
Find the juicy bits.
Exactly. Find those truly interesting insights. Okay, let's unpack this.
So maybe let's set the scene first. What was the landscape like for high-res generative modeling before STARFlow? The paper's intro paints a picture dominated by those two main heavyweights.
Right. First, you've got diffusion models, known for just incredible image quality. Models like ADM, LDM, or the Transformer ones like DIT, SAT, they really set the benchmarks for fidelity.
Absolutely. They operate really smoothly in continuous space, which helps deliver that amazing detail. But like you mentioned, the trade-off is often speed.
Yeah.
Their whole process involves many, many iterative steps of denoising. That makes both training and, importantly, generating images pretty computationally intensive.
Slow.
Definitely slow.
Yeah.
And then the other camp, autoregressive methods. These took a lot of inspiration from the success of large language models, didn't they?
They did. They kind of treat images like sequences of tokens, predicting the next piece. You see models like VAR and MR mentioned in the paper in this category.
So what's their advantage?
Well, their appeal is often that they avoid that iterative denoising. They do this by modeling the image in a discrete space. So they quantize the image data first.
Okay, turn pixels into tokens, essentially.
Yeah, exactly. And this can be faster for sampling sometimes. But that quantization step, turning continuous pixel values into discrete tokens, that can sometimes limit the ultimate fidelity you can achieve compared to models that stay fully in continuous space. Right, you lose some information in that step. And this is where normalizing flows, or NFs, come in.
Precisely. The paper points out that NFs are this powerful family of models based on explicitly learning the probability distribution of the data, what's called the likelihood.
Okay.
They've been around with earlier work like TARFlow mentioned as a starting point, but they just haven't been at the forefront of this high-resolution race until now, perhaps.
So the big question this STARFlow paper is asking really is, can normalizing flows be scaled effectively? Can they produce high-resolution images that are actually competitive with the best diffusion and discrete AR models out there?
And their answer seems to be a pretty definite yes. STARFlow is presented essentially as the first successful demonstration of applying normalizing flows at this kind of scale and resolution and hitting competitive performance marks while doing it.
So it's positioned as a real alternative.
A really interesting alternative, yeah. Because it's a normalizing flow, it naturally supports exact maximum likelihood training that's a nice theoretical property.
Yeah.
And importantly, it operates entirely in continuous space.
So it avoids that quantization issue you mentioned with the discrete AR models.
Exactly. It sidesteps those potential fidelity compromises that can come with quantization.
Okay, so if NFs can scale, what was the secret sauce? What were the specific technical breakthroughs that the Apple researchers came up with to make STARFlow work so well at this level? The paper seems to highlight 3 key innovations.
That's right. The first one is a really clever architectural idea they call the deep shallow architecture.
Deep shallow, okay.
Yeah, they had this intuition, apparently from looking at previous NF models built with transformers, that most of the the heavy computational lifting, the really important transformations, seem to be happening in the first few layers.
Interesting. So not evenly spread out.
Not evenly spread. So instead of just stacking, identical transformer blocks one after another, they designed this structure they denote as LT.
LT. What does that mean?
It means using one very deep transformer block right at the beginning. That's the O layers part. And then following that with T1, much shallower blocks, each only 2 layers deep.
Okay. One big block, then several small ones.
Exactly. The idea is that the deep block handles the initial complex modeling. You can almost think of it like a Gaussian language model generating the core latent representation.
And the shallow ones?
The shallower blocks then refine this initial latent. They act more like a learned image tokenizer, adding finer details, but without needing massive computation at every single step.
Gotcha. And that's where the efficiency king comes from, right? Those shallow blocks must be significantly cheaper computationally.
Way cheaper. And what's also quite neat is they found you only really needed to condition the deep block with external information, like class labels or text captions.
Oh, you don't need to feed the condition into every block.
Apparently not, at least not without hurting performance. This simplifies the whole model architecture. And it even opens the door, potentially, to using pre-trained language models to initialize that deep block.
Interesting possibility. Okay, so that's the architecture. What's the second innovation?
The second crucial piece was embracing learning in the latent space of pre-trained autoencoders.
Okay. This sounds familiar, like latent diffusion.
Exactly like latent diffusion. The principle is the same. Trying to model images directly, pixel by pixel, especially at high resolution, is incredibly difficult and needs huge amounts of resources.
Yeah, the dimensionality is massive.
It's just far more effective to work in a compressed, lower dimensional latent space. So STARFlow adopts this by using pre-trained autoencoders they specifically mentioned, using the VAE encoder and decoder from Stable Diffusion 1.4.
Okay, so they borrow that component.
They borrow that component to map the images down to a much smaller latent representation. And that's what the normalizing flow actually learns to model.
Makes sense. It's a much smaller space to deal with.
Right. And a valuable observation they made was that normalizing flows seem inherently quite well suited to modeling the distributions you find in these compressed latents.
Oh, interesting. Why is that?
They don't go into huge detail, but it seems the structure of NFs aligns well. They also found, building on other NF work, that injecting a bit of carefully controlled noise into the latents during training is pretty important for making the whole process stable.
Okay, so noise helps stability. How does that feed into the training?
Well, it leads to their specific training strategy. They trained the normalizing flow part, the autoregressive flow, to essentially be a prior distribution for these noisy latents.
So the flow learns to generate the noisy latents.
Correct. And then at the same time, they fine-tune the decoder part of the pre-trained VAE. They use standard image quality losses, L2, perceptual JN losses, to make sure that decoder becomes robust enough to generate high-quality images from the potentially noisy latents that the flow samples.
Ah, I see. So the decoder learns to clean up the noise introduced during training.
Basically, yes. And this streamlines the whole sampling pipeline compared to some older methods that might have needed extra gradient-based denoising steps after sampling from the flow.
Okay, that makes sense. Architecture, latent space. What's the third key innovation?
The third one focuses on generation quality, especially when you're guiding the model, like for text to image. They develop a novel guidance algorithm, which is an improvement on classifier-free guidance, or CFG.
CFG. Yeah, that's pretty standard now across generative models, isn't it? To boost quality and appearance to prompts.
It is. It works by amplifying the difference between the conditional prediction, like based on text, and an unconditional one, pushing the sample more strongly towards the guidance.
But the paper says there were issues applying CFG to previous autoregressive flows.
Yeah, apparently it sort of worked, but the underlying theory wasn't fully solid, and critically, it became unstable if you tried to crank up the guidance weight.
Which you often need to do, right? For really good text-to-image results.
Exactly. You need those higher guidance weights for compelling instruction-following images, and the old method just couldn't handle it reliably. The paper shows examples where it breaks down.
So what's their fix?
Their new approach goes back to the roots of CFG, looking at it from the score function perspective, which is how it was originally understood for diffusion models. They derived a new, specific formula for applying guidance tailored to the Gaussian distributions that they're deep block models.
Okay, a more principled derivation for AFs.
Right. And the key fix for that instability problem, it's actually quite simple but brilliant. They clip the ratio of the conditional variance to the unconditional variance so that it's always between 0 and 1.
Clip the variance ratio. Why does that help?
Well, intuitively, guiding a model should make the output distribution more focused, more mode-seeking, right? It should be less spread out than the unconditional distribution.
Yeah, that makes sense. Sharper peaks.
So the guided variance should probably be less than or equal to the original conditional variance, which implies that ratio should be less than or equal to 1. And mathematically, forcing it into the 0, 1 range prevents the denominator in their guidance formula from getting close to 0 or going negative, which was the source of the instability at high guidance strengths.
Ah, clever. So it's both intuitive and mathematically sound.
Exactly. And the result is that this improved CFG is far more stable and effective. It allows them to use strong guidance weights, getting higher quality and more text-aligned images over a much wider range than was possible with previous AF guidance methods.
That's a significant improvement for practical use. It's fascinating how these three pieces, the architecture, the latent space approach, and the improved guidance really came together to make STARFlow work.
Absolutely. But beyond just the clever engineering, the paper also touches on the theoretical underpinnings. They provide some justification for why normalizing flows should be capable of this kind of scaling in the first place.
Okay, so what's the theory?
They revisit the concept of universality for autoregressive flows. This is the idea that, in theory, if you design them right, these models can learn to represent any continuous probability distribution, no matter how complex.
The ultimate flexibility, basically.
Right. And they prove a specific result, Proposition 1 in the paper, which states that stacked autoregressive flows can be universal approximators, but there's a condition.
What's the condition?
They need to have at least 3 blocks, so TO3 in their notation, and they need to use alternating variable orderings between the blocks.
3 blocks minimum. Why not 1 or 2?
Well, they sketch out the reasoning. A single block, T1, is just too simple. Each step is basically just modeling a single Gaussian transformation, which can't capture really complex multimodal distributions like you find in images.
Okay, too limited. What about 2?
2 blocks, T2, gets you much closer. It's almost sufficient. But they show it technically fails universality on the very last coordinate or dimension it processes. Because of the flow structure, that last variable's distribution ends up depending on a unimodal Gaussian, inheriting its limitations.
Ah, a subtle but important failure point.
Exactly. But adding that third block, T3, breaks that limitation. It injects enough sort of fresh latent variables and flexibility throughout the flow that every conditional distribution the model learns can become complex enough technically, an infinite mixture of Gaussians to represent any shape needed.
So that third block unlocks full universality.
That's the claim. And this theoretical grounding gives confidence that autoregressive flows can fundamentally represent the complex distributions needed for high-resolution images. It suggests scaling them up isn't just an engineering hack, it's theoretically sound.
Okay, theory is great, builds confidence. But let's talk results. Performance and results. How does STARFlow actually stack up against the models we know?
Right, the proof is in the pudding. The paper provides pretty comprehensive benchmarks.
So on class-conditioned ImageNet, which is a standard benchmark everyone uses,
They do very well. On 256 by 256 images, they report an FID score of 2.40. FID measures image quality and diversity. Lower is better.
2.40, how does that compare?
That's right. In the mix with state-of-the-art diffusion models like DIT 2.27 and SINT 2.6, and top autoregressive models like VAR 1.73 and MORE 1.55. So highly competitive.
Okay, what about high resolution? 512 by 512?
At 512 by 512, STARFlow gets an FID of 3.00. Again, very comparable to DIT 3.04 and MASS-DEET 2.50. Although it's fair to note some very cutting-edge diffusion models like EDM2 get even lower FIDs, down near 1.25.
Still, pretty impressive for a first large-scale NF model.
Definitely. And they make an interesting point in the appendix. They say their FID score is very close to the best possible FID their fine-tuned V80 decoder can achieve, even when given perfect noisy latent inputs. Meaning the normalizing flow part itself seems to be doing a really good job modeling the latent space distribution. The bottleneck might be more in the decoder they used.
Gotcha. Okay, what about text-to-image generation? That's arguably even more important these days.
Yeah, they tested that too, using datasets like Kosho for zero-shot evaluation. Their full STARFlow model achieves an FID of 9.1.
9.1 FID on Kosho zero-shot. How does that rate?
Again, very competitive. It matches models like GigaGAN also 9.1, and sits nicely alongside other big names like Imagen around 7.3 and Parti 7.2 and eDiff-I 7.0. It confirms STARFlow isn't just good at class conditional stuff, it can handle the complexity of free-form text prompts.
And just looking at the pictures, the qualitative results.
They look really good. The paper shows examples in figures 7, 8, and 9. You see high-resolution images, they support different aspect ratios, and visually the perceptual quality seems right up there with what you'd expect from top-tier diffusion or AR models today. Clean, detailed, coherent.
Okay, quality is there. What about inference speed? That was the big drawback mentioned for diffusion.
Right. So diffusion models are typically the slowest because of all those sequential denoising steps.
Yeah.
Many steps.
Yeah, sometimes hundreds or even thousands.
Exactly. Autoregressive models in STARFlow, because they're based on transformers, generally have a lower computational cost per token or per latent variable step.
Okay.
The paper shows STARFlow actually outperforms a basic AR baseline model, especially at larger batch sizes. They suggest this is partly because their guidance is restricted just to the deep block and they remove some overhead from standard AR sampling.
And the deep shallow design must help too.
Definitely. They explicitly compare it in Table 5. Their deep shallow model is significantly faster for inference than a hypothetical equally large AF model built with uniform blocks, something like 35 seconds versus 72 seconds for a batch on their hardware.
So faster than diffusion and potentially competitive with, or faster than some AR approaches depending on implementation.
That seems to be the takeaway. And they also did solid ablation studies to back up their design choices.
Right, checking if the pieces actually mattered.
Yeah. These studies confirm that the deep shallow architecture really is beneficial for both efficiency and final performance. And they show their specific variant of CFG is indeed much more stable and effective across a wide range of guidance strengths compared to just naively applying prior CFG methods to autoregressive flows.
Good to see that verification. Now, one of the really cool things about normalizing flows is their mathematical structure. Does that enable anything beyond just generating images?
It does. That's a key point the paper makes. STARFlow's architecture and the inherent properties of NFs open up some really interesting applications beyond symbol generation, often without needing entirely new models or lots of extra training.
Like what?
Well, the first one they demonstrate is training-free image inpainting.
Inpainting, so filling in missing parts of an image. How does that work without training?
Because the model is invertible and works in latent space. You can take your masked image, use the VAE encoder to map it into the latent space. Then in that latent space, you replace the area corresponding to the mask with random noise. And then you use a clever iterative sampling technique. They mention something like Metropolis Hastings operating in the latent space guided by the normalizing flow. This process essentially fills in the noise in a way that's consistent with the surrounding latent representation and the flow's learned distribution while keeping the unmasked parts fixed.
Ah, so the flow guides the filling in process based on what it learned about natural images.
Exactly. And the key is, you didn't need to train a separate model specifically for the task of inpainting.
That's pretty neat. What else?
Well, this leads naturally to another really compelling application: interactive generation and editing.
Okay, editing existing images or guiding generation interactively.
Right. By fine-tuning the STARFlow model slightly on an editing dataset, they mentioned one called ANI-AIT, you can use a single conditional STARFlow model for both generating images from scratch and performing edits based on user input.
A single model for both. How?
This is where that unique property of normalizing flows, their invertibility, becomes incredibly powerful.
The fact that you can run them forwards and backwards easily?
Precisely. Unlike many generative models where encoding an existing image back into a useful latent representation for editing can be tricky, approximate, or require separate networks, an NF lets you do it directly.
So you can take the user's image,
run it forward through the flow and VAE encoder in a single pass to get its exact latent representation. Then apply the edit in that latent space based on the user's instruction, and then run that modified latent backward through the flow and VAE decoder in a single reverse pass to get the final edited image.
Wow, a single forward pass to encode, manipulate, single reverse pass to decode?
Yeah, they call it the single pass round trip property. It's incredibly efficient for interactive workflows and fits really naturally with the transformer architecture they use. Way more direct than diffusion-based editing often is.
That sounds like a significant advantage for creative tools.
It really could be.
Okay, so bringing all this together, what does this work on STARFlow really mean? What are the bigger implications for the future of AI, particularly in generative modeling?
Well, I think fundamentally it shifts the perspective on normalizing flows. quite dramatically. They're clearly not just a theoretical concept or something limited to simpler, lower resolution tasks anymore.
Right. STARFlow really proves they are a viable, scalable, and crucially competitive paradigm for state-of-the-art high-resolution image generation.
Exactly. They now stand alongside diffusion and autoregressive models as like a third pillar, a core approach you have to consider.
And it strongly validates that strategy of working in latent space, doesn't it? That seems key for scaling NFs to high resolutions, just like it was for diffusion models.
Absolutely essential, it seems. But beyond just matching the others, STARFlow highlights the distinctive strengths that normalizing flows bring to the table.
Yeah, like what?
Well, we talked about the exact log likelihoods.
Yeah.
That's useful for rigorous evaluation, maybe different kinds of trading objectives down the line.
Principled learning.
Right. Then there's that unique invertibility we just discussed.
Yeah.
That's a huge potential advantage for applications like interactive editing, image manipulation, maybe even things like compression.
Yeah, that round-trip property is compelling.
And third, they offer pretty efficient inference compared to diffusion models, even if there's maybe still some room to optimize compared to the absolute fastest standard AR methods. It's a strong point.
So this work definitely feels like it reignites serious interest in NFs. They're back on the map as a fundamental method in the generative AI landscape.
I think so. Of course, the authors themselves mention areas for future work, like could you jointly train the VAE and the flow instead of relying on a pre-trained one?
Good question.
Could you push inference speed even further, maybe using techniques like distillation or speculative decoding? Can this approach be generalized effectively to other modalities like video or 3D data?
All important next steps.
But the main takeaway for now is that NFs, through STARFlow, have really arrived at the top table. They've earned their place.
It adds a distinct, powerful tool to the generative AI toolbox, and it makes you think. When you consider the future of AI systems that need to do more than just create images, systems that might need to deeply understand, manipulate, maybe even reason about visual content, could the unique properties of NF, especially that easy invertibility and the exact likelihoods, become incredibly valuable, maybe more valuable than we currently appreciate?
That's a fascinating thought. Being able to efficiently and exactly move back and forth between the pixel space and a meaningful latent representation that could unlock possibilities for different kinds of interaction, maybe better integration within larger AI systems that the current dominant paradigms might not support quite as naturally.
All right. So to wrap up this deep dive then, STARFlow represents a major achievement. It demonstrates convincingly that normalizing flows, by cleverly combining autoregressive structures with transformers, leveraging latent spaces, and developing smarter guidance techniques, can achieve genuinely state-of-the-art results in high-resolution image generation.
It's a fantastic example of how established techniques can find new life and reach new heights through smart scaling, architectural innovation, and tackling bottlenecks head-on. A clear sign the field is still full of diverse ideas.
Absolutely. So here's something to think about. Given that STARFlow demonstrates these practical benefits of normalizing flows, things like single-pass editing and exact likelihoods, how might this fundamentally different approach influence the future development of AI systems, especially those that need not just to generate, but also to truly understand, manipulate, and perhaps even reason about the visual world? What unique applications could be unlocked by generative models offering these specific properties, potentially challenging the diffusion or discrete AR paradigms that currently dominate the field?